About them their homework. How many of you did the homework? 2 people. Good thing we have a week off. That's okay. You guys could go, hey, Miss Schoenherr, how's the grading going? Oh, yeah. So don't worry. I can dish it out, but I can take it too. You guys, But any last chance? Any questions on the homework? Anyone? Yes. Yes. Whoop, over here. Was there a particular part or just the whole thing? So kind of the whole thing? Just the green work? I'm sorry. Okay. So we're going to use the ratio test to find the interval of convergence. If I let a sub n be that, and actually, I don't really need the -1. I put it there. Either way, it's going to work. Because once we put the absolute value on, it gets rid of the -1 to a power, and I get down to here. So, any questions just on that part? Right. So then, finding the radius of convergence, the radius of the root 2 words. Hard. Yeah. But now we have to check the endpoints, because it didn't want the radius of convergence. It wanted the interval. So checking the endpoints, putting in a -√2. So there's a couple of things here that are kind of weird that may have been the question. So one thing is I can definitely take off the -1 out of here. I got -1 to the 2n plus 1. Plus n should be -1 to the 3n plus 1, but I just wrote n. Wait, what? That's because if you think of, and you could have written 3n plus 1, it wouldn't have been wrong. But if you think of 3n plus 1 and then let n equal 1, 2, 3, and so on, the values alternate between an even and an odd number. And so it's equivalent to saying -1 to the n, and I just made sure I started with the right sign. But that's why the exponent doesn't seem to match. All right, n plus 1, I guess I did. So we got that. Other thing is, remember back over here. Yeah, I didn't put there. When you take the negative out, you still have the square root of 2, which is 2 to the 1/2. So 2 to the 1/2 to the 2n plus 1, multiplying the exponents, and you get that. So any questions on how I was able to simplify it? And then it's just an alternating series, which passes the test, so it converges. I think the square root, the positive one, was easier to understand because I didn't have that weird -1 thing going on. But this guy, when you have a positive root 2, it's still is an alternating series. And I admit I got a little lazy and didn't feel like writing all that out again, so I didn't. Probably not the best role model there. Sorry. Anyway, but there's the interval. Any questions on that? Or anything else? Oh, yes.
When you took the sign of the exponent, how did you get to x squared? A little bit further up the circle.
Oh, that's not covered. Up there at the top?
Yeah, I think when we're simplifying the absolute values.
Oh, so let me bring it down a little bit more so I can point. This part right here would be like, so this is 2n plus 2 plus 1, so that's 2n plus 3. This is 2n plus 1.
Oh, wait, and then division is subtracting.
Yep.
Okay, thank you.
Any other questions? Either on this or anything else? Well, then let me have your homework. And no reality check. I think I heard some people saying that. Yeah, minimum day. Not necessarily because it's a minimum day, but it's a minimum day where I got a lot of other stuff I want to do. We don't got time for no reality check. Yeah. Oh, I think you very much.
Basically, I'm going to I know, it's not. Look, you're missing B, C, D, and F. Well, it's missing B, C.
Just say 5. Just say 5.
Just say 5.
I wonder if the microphone picks up your voice.
What? I hope it does, so that everyone knows it low. C. E, F, G, and H, and I.
All right, so let's do this. Oh, actually, I have a present for you guys. Yeah. It's a reality check after all. Just kidding. So big.
Why?
So I take no responsibility for this. Something I found on the internet years ago, but hey, little handy. Look at this. AP Calculus. Stuff you must know cold. Oh, wow. It goes front and back. This is awesome. Look at all this stuff you got to know. You already know a lot of it. Some of this, actually, we're about to learn, anyway, a lot of it. But just a little reference sheet. Something for you guys. But, let's, show the notes. What do we got here? We're doing section 10.7 today. This is actually the last section. Yo. Now, when we come back, I'll see you on Tuesday. So we're still going to do a little something with this section. And then Thursday, we're going to do a little, well, it'll be a You Do You review day. And then the following Monday, where you celebrate. Yeah! So this is section 10.7, Taylor series. And yes, we did cover Taylor polynomials already. These are very closely related. So, let us recall. A Taylor polynomial to approximate a function f of x centered at x equals c is bum bum bum. So if we have our nth degree polynomial, we start with f of c, and then it's f prime of c over 1 factorial plus f double prime of c. I need more room. Oh wait, I forgot something. What am I doing? Uh-oh! What did I forget? See, I was just checking to make sure you guys remembered, and you did. Good job. I wish I could say that was true. And this just keeps on going until we get to the last term, and since this is an nth degree polynomial, it will be the nth derivative of c over n factorial times x minus c to the n. Yay! So Taylor polynomial is finite. It stops. Godzilla! Anybody play Animal Crossing? I was really excited when, I saw, this is like old. This is like from the beginning of Animal Crossing, but in the Nook shop, how they got the monster, but he looks like Godzilla, because it just makes me happy. Yeah. And I made the robot, and so like right outside my house, the robot and Godzilla, I have to go like in the morning when I do Animal Crossing. My very first thing I do is I go out the house and I make them fight each other. Yeah. It's my favorite thing. I'm easily amused. What can I say? All right, so the term Taylor series. Anybody still playing Animal Crossing? I am. I'm finally getting the $300 out of my Switch. I don't play games typically. I don't know why I actually don't know why I bought a Switch. I had it for years, and then Animal Crossing came out, and then I finally started playing it. The term Taylor series is typically used to refer to the infinite sum. I mean, technically, a Taylor polynomial is a series because you're adding up a bunch of terms in a pattern. It's just a finite series. But when people talk about Taylor series, they're usually talking about the infinite sum. So we're going to do the summation as n goes from 0 to infinity. And then we're going to write the nth term. So it's the nth derivative at c over n factorial times x minus c to the n. Ta-da! Pew, 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 pew. Now, we've gone through the whole, like when we talked about a Taylor polynomial, how to find these things. You have to go through, like, find all the derivatives. And then you evaluate all the derivatives at c. And maybe there's a pattern, maybe there isn't. Blah, 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 blah. So, there are some, though, that you should just know. Boom. And you don't have to, boom, show any work on the AP exam or on my tests if we ask about them. So, and they're actually on your stuff to know cold. Although, honestly, so I think it's on the back. Yeah. If you look on the back side in the lower left corner, it says Maclaurin series. And they actually give 5 of them. The last one is natural log of x. As soon as I say I've never seen it, I don't recall seeing it on the AP exam, you don't have to know it. They're going to put it on this year's. I mean, so I'm not going to say that. I'm not going to put it on mine, though, unless I want you to, like, derive it. But the ones you should know cold, memorize these. For the AP test and show and here's test. Show and here's celebration. E to the x. And you can see e to the x right there. Excuse me. It's 1 plus, I'll just say 1 plus x squared over 2 factorial plus, excuse me, x cubed over 3 factorial plus x to the 4th over 4 factorial plus, and we can also rewrite this as a sigma and say as n goes from 0 to infinity, it is x to the n over n factorial. And the radius of convergence is infinity. This converges for all x. So even though this is centered at x equals 0, it's okay if you're going to use this to approximate something not close to 0. It may take a lot longer to converge to the actual value. The closer you are to 0, the faster it's going to converge to the actual value. But it will eventually converge for all values of x. So know that one. Know sine x, which is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus... So it is an alternating series, and then it uses the odd numbers. So we could write that as a summation as n goes from 0 to infinity. So first of all, we have the alternating sign, so I'll say -1 to the n. And then it is x to the 2n plus 1 over 2n plus 1 factorial. And this one also converges for all values of x. And then we have cosine. And the cosine of x. Sine uses the odd powers. Cosine uses the even powers. So we start with x to the 0, but that's just 1. And then it's minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus and this guy then is negative 1 to the n, x to the 2n over 2n factorial, and it also converges for all values of x. And then there's one more, which we actually covered last class. 1 over 1 minus x. And that's just that geometric series. So it's 1 plus x squared plus x cubed plus as n goes from 0 to infinity. And then this is just x to the n. And this one does not converge for all values of x. Finally, we get to write something different. As long as x, the absolute value of x, is less than 1. Now you'll see, like, if we just memorize them, then what else do we do with them? You're going to see that in a minute. Your homework is going to use other series besides just these 4. On page 599, actually, this is not to memorize, but for the homework, also look at page 599 for other series that you can use in the homework. So, let's see. We just have 3, maybe 4 examples, and then that'll be the notes. We'll see how time goes. 4th example isn't vital. Anybody need anything on this page? All right, let's do it then. First example. Derive the Taylor series for cosine. Actually, let's say for sine first. For sine, I don't know what order. Anyway, derive the Taylor series for sine x using cosine x and vice versa. What does that even mean? I don't know. I read it on the internet. No. Okay. Let's just start with sine. I'm going to rewrite the thing. Actually, try not to look. From just writing it one time, do you remember what the expansion is for sine? Karen?
It's negative 1 to the n times x to the 2n plus 1 over n plus 1, 2n plus 1.
Nice, yeah. You got it. All right, so it's going to be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. So this is just what I gave you on the other page. So here's one thing we can do with it. You can differentiate and integrate these term by term, is what it's called, because you do it term by term. So, the derivative of sine x will be the derivative of, and I'll just do the expansion part, x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus so we just differentiate. And theoretically this is supposed to work. Let's see if it does. What's the derivative of sine? Cosine. And what's the derivative of x? And the derivative of x cubed over 3 factorial. Yeah. It will be x squared over 2 factorial, because if you think about it, we know we multiply by the exponent, so that's going to bring the 3 out in front. But then the 3 on top is going to cancel out with the 3 on the bottom and just leave us with, holy crap, 2 factorial. This is crazy! And then sure enough, the next term, that 4 that we would multiply by or the 5 that we would multiply by cancels out with the 5 in the bottom, and then we're left with 4 factorial. And hey, did this work? Is this the series that I gave you for cosine? Yeah, and in fact, if we take a look at the summation, I'm just going to go up here and just rewrite the summation for sine, but we're taking the derivative of it. Make sure you put d dx out in front. But if we apply our differentiation rules to this argument, it's going to work. Now remember, we're differentiating with respect to x, so x is going to be the variable. So the first thing in this -1 to the power of n, that doesn't have an x in it at all, so that's going to be like a coefficient that just comes down for the ride. And then if we follow the rules for the power rule for differentiation, multiply by the exponent, decrease the exponent by 1. So multiply by the exponent and decrease the exponent by 1, but then it's still over this 2n plus 1 factorial. And then, just like we were seeing in the terms before, the 2n plus 1s on the top and bottom, they cancel out. And then we're left with the thing I gave you for cosine on the other page. Godzilla. So, the moral of the story is, let's say you don't have the whole expansion, you just have the series written as a sigma. You can still apply your integration and differentiation rules to just the argument and the sigma, and it's going to work. Now, one little caveat is the limits. It's not really a caveat, but sometimes you will see people, where is it? There it is. We're starting at n equals 0. Sometimes you'll see, wait a minute, the 0 just changed to a 1? Why? How did that happen in the work? So if you check it, you'll see that it's happening because that first term, you don't actually need the n equals 0. Usually it's because that first term ended up being 0. Doesn't happen on this one. Because, yeah, on this one we're going to need it. But imagine if we had like just x to the n. Imagine if we just had sigma of x to the n. When you do the derivative, you'd have n x to the n. If you're starting at 0, the first term is just 0, so people will sometimes just leave off the n, letting n equal 0 and just say, let's just start at 1. That's why their lower limit is changing. So don't get like, wait, why is it sometimes changing and sometimes it isn't? That's the only reason. But we're going to go ahead and still stick with the 0 and infinity. So, if you know one series and you're trying to derive another series from it, you can differentiate and integrate if you want. Any questions on that? Yes, we have to do the other way, but
Yes. Totally unrelated, but if you have 2n factorial without parentheses, what's the order of operations?
It would just be n factor. It would be 2 times the factorial of n. All right, so now let's go ahead and start with cosine. So cosine we have right above. And actually, I'll just do the sigma. So we know cosine is, the sigma is n goes from 0 to infinity of -1 to the n times x to the 2n over 2n factorial. Now, if we tried to differentiate, let's try to differentiate. Maybe this will work. Who knows? What's the derivative of cosine? Yeah, be negative sine. Oh, I forgot the ddx. Squeeze it in there. All right, so let's see what happens when we do this. You guys tell me. Follow your differentiation rules. What's the power rule for derivatives? It's not a trick question. If you're like, where's she going? What's the derivative of x to the power 5? Right. So you multiply by the exponent and decrease the exponent by 1. The -1 to the n over 2n factorial, that doesn't depend on x. That's like a coefficient that comes down for the ride. So we're only going to do power rule on just the x to the 2n. So times 2n, multiply by the exponent, and decrease the exponent by 1. And then the 2n's will cancel. -1. And so we have x to the 2n minus 1 over... What happens when we cancel out the 2n's? What are we left with? Anybody see a problem yet? What's the problem? Yeah, and one of the big problems here is if n starts at 0, what's -1 factorial? Crap. Can't take the factorial of a negative. So in this case, the derivative thing doesn't work. Can't take the factorial of a negative. We're going to have to integrate instead. By the way, just totally unrelated to this, you can expand the idea of factorials to something that's called the gamma function. And then the gamma function extends to all real numbers. Factorials are just for non-negative integers. Gamma function lets you do all real numbers. But anyway, this is not the gamma function, this is factorial. So differentiation didn't work. Let's do integration. Going back here. Ba, 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 da, da, da. I'll just draw a blank. X to the 2n over 2n factorial. N goes from 0 to infinity. So let's try integrating instead. So we'll integrate. Whoop. And see what happens. What's the integral of cosine? Sine. By the way, one little note. I mean, you guys probably would have figured this out anyway, but on the other thing, if the differentiation was working, I mean, we weren't getting exactly sine, we were just getting a negative, but that's okay. You could just multiply both sides by -1 and things would have been good. All right, so follow the rules then for the integration rule for powers. That's where I just lost my marker. Again, the -1 to the n over 2n factorial doesn't depend on x. That acts like a coefficient. That comes down for the ride. But now we're going to do the power rule for integration, where you add 1 to the exponent and then divide by the exponent. Come back here. There it is. So we're going to add 1 to the exponent and then divide by that exponent. Hey, check it out. Because if I have 2n factorial and I just go 1 more to 2n plus 1, looks like I'm going to get 2n plus 1 factorial. And that is our formula for sine. So that worked. Yes. So, a cool little thing you can do with these. You can integrate and differentiate. Any questions about that? Alright then. Here's another thing. This goes to 10:35, right? We've got time. We're doing good. Alright, example. Determine a power series for the sine of x squared centered at x equals 0. This is a nice, easy problem. Easy peasy, lemon squeezy. Who came up with that? I don't know. I like it, though. Well, I don't know the sine of x squared, but we know the sine of x. After today, you're going to know that one. If you don't already have it memorized, you're going to. I'm going to go ahead and just write it as a sigma. So, it's the same thing we've been writing over and over and over again. The summation of -1 to the n times x to the 2n plus 1 over 2n plus 1. So, what would, what would the sine of x squared be? What do you think? Anybody got an idea? Yeah, plug in x squared. Replace the x with x squared. It's really that easy. And then simplify if you can. This guy we can simplify a little bit. Sine of x squared is power to a power, just multiply the exponents. So it's x to the 4n plus 2 over 2n plus 1 factorial. Mic drop. If only all your homework was like that one. But you do have some of those. So that'll be nice. Yes?
Power series is the same thing as a Taylor series.
Yeah, a Taylor series is a specific type of power series. Remember, a power series is anything that's written like this. Oh, you see. And a Taylor series defines a sub n as the nth derivative at c over n factorial. Any other questions? All right. Possibly our last question. We'll see. This is definitely the meatiest question, though. Express the definite integral as an infinite series and find its value to within an error of at most 10 to the negative fourth. The definite integral is the integral from 0 to 1 of tan inverse of x squared dx. And this is a good example, like on your homework, you're going to have a problem like this. And if you go to page 599, you will see that, oh, well, look, tan inverse of x is the summation as n goes from 0 to infinity of negative 1 to the nth power, x to the 2n plus 1 over 2n plus 1. Looks very familiar, doesn't it? Looks a lot like sine, except no factorial on the bottom. So there'll be times when it's used in a series, you're like, wait, let me, like, it's not e sine, cosine, or 1 over 1 minus x. Go look at page 599 and see if it's something on their table there. Okay. We can do this. So, the first thing you're going to do, let's just start with tan inverse of x. So, tan inverse of x, I'm just going to rewrite the sigma. So we got that. But we're not dealing with tan inverse of x. We're dealing with tan inverse of x squared. Crap, what do we do? Nicola, what do we do again? Yeah, same thing you said last time. Just let x equal x squared. Sorry to put you on the spot like that. But yeah, he handled it with grace. He's awesome. So we're going to take the x and make it an x squared, if I can write it too. And all I'm going to do is just multiply those exponents. So it's x to the 4n plus 2. All right. So any questions so far? Godzilla. But we're not dealing with the tan inverse of x squared. We're dealing with the integral of tan inverse of x squared. I wonder what we do next. Integrate. Now it is a definite integral, so I'll put the limits on. It's the integral from 0 to 1 dx. The integral, that was what was given. The part in black or dark blue up there. Black, dark blue, whatever. Dx. Alright, so now we're finally dealing with what we want to deal with here. So I'll just go ahead and rewrite the left-hand side. But on the right-hand side, we got something to integrate. So it'll be the summation as n goes from 0 to infinity. Anybody know? Anybody want to give it to me? Either the numerator or the denominator or both? What happens to the negative 1 to the power of n? Oh, okay. I don't know where I wrote an x. What happens to the x to the 4n plus 2? Yeah, add 1. So it becomes x to the 4n plus 3. Add 1 to the exponent. Divide by the exponent. So we also have to divide by 4n plus 3. And then we also have the 2n plus 1 from before. I don't need the dx. We integrated. But we do need to plug in the 0 and 1. So any questions there? Now, when we plug in the 1, that's going to be easy. 1 to the power of 4n plus 3, that's just 1. So that's going to make this go away. And then we're left with the other stuff. When we plug in the 0, well, that's going to make the whole darn thing go away. So we won't even have that. So we can say that the integral from 0 to 1 of tan inverse of x squared dx is the summation of negative 1 to the power of n over 4n plus 3 times 2n plus 1 as n goes from 0 to infinity. And there's the power series that represents our definite integral. Yay! So we've answered the first part of the question. But any questions? Want a moment to just look at it before we do the other part, which is the error bound. Okay. Hearing nothing, let's look back at the problem again. So we expressed it as an infinite series. We got that. Now we're supposed to find its value to within an error of at most 10 to the negative 4. We're not actually just calculating the error bound. We actually have to calculate the value. What? All right, let's take a look at this. So we have this series now that we're going to use. And what do you notice about this series? Anything? Like, say, they'll take anything. Ah, and that's it. That's the key right there. This ends up being an alternating series. And I believe we have an alternating series error bound. Oh. We might. Hey. This is an alternating series. And we know that, I don't know, what do we know? We know that the difference between the actual sum and a partial sum has to be within, what was, yeah. Remember the next term, leaving out the negative 1 to the end. And we're saying that the problem says we want the error to be within 10 to the negative 4, so we actually need this to be less than or equal to 10 to the negative 4 for this particular problem. So now we got it. We know what a sub n is, so I should use a capital if I'm using a capital on the other. All I'm going to do is take this thing, forgetting about the negative, let all the n's be n plus 1. So 1 over 4n plus 1 plus 3 times 2n plus 1 plus 1 has to be less than or equal to 10 to the negative 4. And now we have something to solve for n. First thing I'm going to do, I'm going to make it a little easier to deal with. I'll flip both sides. And I'm also going to distribute. So if I flip the left-hand side and distribute, we're going to get 4n plus 4 plus 3. So that's 4n plus 7. And 2n plus 2 plus 1, 2n plus 3. And if I flip it, remember I got to flip the inequality also. So I get this. So now, how am I going to solve it? Honestly, brute force. Somebody take a guess. Give me a number for n. 7. Okay. What I'm doing on my calculator, it'll take too long to like set it up. I'm storing 7 into x on my calculator to make this easy, because I'm going to reevaluate this thing over and over and over again. So now that x is 7, I'm going to ask my calculator, hey, what is 4x plus 7 times 2x plus 3? So, when n equals 7, 4n plus 7 times 2n plus 3. This is 595. Is that good enough? All right. So give me another number. 10,000 might be a little big. 20? 20 store x, and then I can just do it. So if n is 20, we're getting 3,741. Is that big enough? Okay, keep going. Like this is literally, there's no other shortcut. 100? If we're at 100, we get 82,621. That is big enough, but maybe we can get a little closer. Let's see how close we can get. So something between 20 and 100. How about not 69? Did you of all people say that? How about, it's somewhere around here. I can't remember it. So just, for sake of time. 33 would give us 9,500. Yeah, anyway, I can't say the number. So yeah, 34 must have been it. Yeah. Hey, there we go. So we're going to use the 34th partial sum. So we're going to use the summation as n goes from 0 to 34. I don't even remember what it was. Negative 1 to the n. Hey, back here. Over 4n plus 3. 4n plus 3. 2n plus 1. And then we're going to have the calculator work this out. Do you guys know where to get the summation on your calculator? On your calculator, if you hit math, and I think it's 0. But yeah, math 0. I'll put it here. Math 0 on the calculator. And when you do that, it literally pulls up a sigma that you fill in. So 0 to 34, and then you got to plug this whole thing in. Let me just make sure I type this in right. Yeah, it looks right. And it's about 0.297953. There you go. We'll stop there. But any questions? Yes?
So the only reason that you wouldn't want the n to be like 10,000 or something is because it would kill the calculator?
No, it's only because I knew the answer.
It also does still calculate.
Oh, it does? Oh,
Yeah,
okay.
it does.
That wasn't because of that. I knew that it was. I remembered it was somewhere around here. I was like, come on, let's get there faster. But theoretically, you could do this on a computer that could handle it. So
Yeah, like, 'cause if you make n like obviously larger than it needs to be, then you don't have to do any of the guesswork.
right.
It doesn't give you the
This.
yeah.
I hope you guys have a fantastic break. Thanks. I think I'm going to do a little work on my New Horizons island. It's a little boring. I haven't changed it in a while. Yes.
Anything you don't play games. There's a really good game on Switch called Hades.
Called what?
Hades.
Hades, like hell?
Yeah.
Okay.
And it's like a. I don't know. If you're in Animal Crossing, I guess it might not be your thing. But Mia really likes Animal Crossing, but she also really likes this game.
All right.
Yeah, it's like a roguelike game. So it's like a bunch of like rooms to go through and stuff. I don't know if that's a thing.
Okay, I'll check it out though. Thanks.
I have a 0 for homework.
I screwed up everybody's. Oh, here, let me freeze the screen. Everybody doesn't need to see everybody's grade. Sorry. You're not the first person. I think I just made a mistake with it. Is it just the E?
It's B.
Oh, no.
I have 2 days homework.
Bye! I don't know what I'm doing. Have a good one, you guys! I know you gotta go here. Is it so B and oh, here, I'll take that one then. But B. Okay, I'll do that. I know you gotta go to the next class, so I don't want to hold you up. I'm changing it right now, though. Bye. Thanks. You too. Bye bye. Thank you. You too. Bye. Thank you. You too. Bye, y'all. You too. Woohoo! Bye-bye! See you later, alligator. Bye, Nikhil. Hello. Woo. Oh no. Freezing apparently doesn't really freeze. Well, who knew that? They'll call you out, though. Yeah. Okay. Thank you for the heads up, though.
What's up?
Everybody else.